So welcome everyone. Today is the 1st of May. We are going to, and this is Wednesday evening in California, 7 p.m. Traditionally, every week we meet at this time and do something interesting. Usually it's a research paper reading or some interesting project walkthrough or some tutorial and so forth. So today's topic is a continuation of what we have been doing in the last two sessions. There is a vision that Jan LeCun presented, which was for autonomous machine intelligence. The core premise of that paper, and we were doing that paper in the past sessions, and it is this paper, we are going to complete this paper today, and then go to V-JEPA, which is the topic for today. In this, he presented the vision that the way we are training these machines to do generative, for example, diffusion models and so on and so forth, pixel generation, the machine is not learning much. The results may be impressive. And the results of, for example, diffusion models truly are impressive. But it is doubtful whether the machine is truly developing a core intelligence. And the question that Jan LeCun asked is, how do human beings learn, and can we in some way simulate or parallel that form of learning in machines? So it's a long thought paper. It spans about 63 pages or so. In this, the core ideas that this paper brings forward is that we need a model, we need a sort of a world model. The machine needs to learn a world model. It needs to understand how things in the real world behave. For example, if you look at a cat and I give you just the body of the cat, it should be able to understand that this is the body of the cat. Therefore, in front of the cat is the head and behind the cat is the tail. Behind that body is the tail. And the tail and the body and the head together make up a cat. That's sort of oversimplifying it, but that is a world model. And that world model, therefore, implicitly is predictive, because if you can identify that you're looking at a cat's body, it is therefore natural to infer that there's a tail behind it and there is a head in front of it. Or if you see half a face with one eye and one eye, you already know your world model helps you infer that there is the other eye adjacent to it. So that is the core idea. Now, in pursuit of the core idea, there are some quite a few deep thoughts that this paper brings forward. One is that it sort of dwells quite a bit on energy models. Now, energy models have been something near and dear to a lot of researchers in machine learning. And Jan LeCun goes on to point out that they have certain reasons to resurrect and to really take these models very, very seriously. And they may be the way forward to solve problems, to help machines learn sort of a world model and develop autonomous machine intelligence. The way a child learns about the world, develops a world model. In the same way, the machine should develop the world models autonomously by, in an unsupervised way, observe the external world, see its behavior, and from that, gradually, by osmosis almost, absorb and distill all of that data into a world model that it used to predict. This paper also makes a strong emphasis that that sort of intelligence's quality will be predictive rather than generative. Generative would be a secondary consequence of a model that is inherently predictive. The next point that this paper makes is that these world models, they sort of exist, or their natural representations are in a latent space. Not in the, for example, if you're talking about images and videos, not in the pixel space, but in a deeper representation space. Now, when you talk of a latent representation space, of course, it harks back to discussions going back to 2006 and Geoffrey Hinton and the whole all of this whole push for representation learning that has been going on now for 2 decades almost. So very much in line with that and reinforcing some of those ideas quite strongly. So that was the paper. I'll just quickly go over it. Now, the way we did our past 2 sessions is we started with I-JEPA. The I-JEPA architecture was a practical architecture of predicting missing parts of an image. What is it that it is missing? And I'll quickly go through that, but not too much, because I assume you folks you have attended. I apologize to those who are attending this session for the first time, but I'll try to fill in enough gaps that it will make sense. So I-JEPA applied this core ideas of doing everything, making prediction models in the latent space.
Are you sharing, Asif?
Oh, am I not sharing the screen? I apologize. So is it better now?
Yeah, it's coming.
So this position or this thought paper is, it says that it makes the following main contributions, 4 contributions, this thought paper. An overall cognitive architecture in which all modules are differentiable and many of them are trainable. Which essentially, now why do we care about differentiability? Because backpropagation becomes possible if it is a differentiable module. Also, most things are trainable, that's good. JEPA is the main thought, the main architecture that it comes up with, a hierarchical JEPA. And then it also makes a point that the learning is self-supervised or autonomous, I suppose. It is a non-contrastive. That point is important. It does not use contrastive learning. Why it doesn't use contrastive learning is because contrastive learning, amongst other things, suffers from the curse of dimensionality. And we'll talk a little bit about it. Right? Now, learning a world model, we went through how human beings learn, a child learns after birth, and so on and so forth. And there's a lot of the Model 1 and Model 2 thinking, or System 1, System 2 thinking, going back to Kahneman's famous book on this thinking fast and slow. So it makes very strongly plausible arguments of how slow thinking with sufficient training gets converted in machines, or can be converted in machines, to fast thinking or instinctive response, as fast thinking is. If you remember, if those of you who have read Thinking Fast and Slow, to most things in life, we respond instinctively, we respond immediately. And that immediate response is protective. Like, for example, if you spot what looks like a tiger behind the bush, you would rather have instinctive response, which would be fight or flight, rather than a more measured, thoughtful response in which you evaluate and debate whether or not it really is a tiger, given all the parameters of what you're seeing. By the time you might have become food for the tiger. So, but there are situations, of course, where instinctive thinking or System 1 thinking misleads us, and System 2 thinking, assuming that you have luxury of time, System 2 thinking is always better. Now, in very easy situations, System 2 thinking may be a waste of time. For example, if you're thirsty and there's a glass of water in front of you, it might not be wise to indulge in System 2 thinking, to first go over when was the last time you had water, what is the reason why you feel thirsty, and how much of the water should you drink. Instinctively, it may be better to follow the first idea and just pick up the water and drink it. So, but generally, when the problem gets complicated, especially when it is of logic and arithmetic, System 2 thinking or more involved thinking helps you get to the right answer. But the point is that the more you practice, the more what is hard becomes easy. And so a lot of the things that come from System 2 thinking gradually become System 1 thinking. For example, cycling or driving are classic examples. We start out by very carefully considering the parameters of the road when we learn to drive, but in no time it becomes almost subconscious ability to drive. And so that's what this paper went into quite a bit, that there's an architecture to make it possible. And we won't go through that architecture, but I think we left at this point. So this picture has become quite central to the ideas that Jan LeCun has been talking about. And I believe I did not cover this part. How do you create world models, the energy model? I'll cover it very briefly and then we'll go straight to the V-JEPA paper. Did I cover this, guys? Do you remember? I forgot entirely where I stopped last time.
We went over this in one of the class, I'm not sure when.
Okay, so I might have gone over this. I'll just use it as a quick review. What in this picture, what what he's saying is something quite simple actually. And now let me get back into my writing mode. Pull the writing mode forward. See what. Let's think more broadly than this picture, and let us say that given input X, there is a response Y. This is how data comes to us, like, for example, in supervised learning, and so forth. So this is the input, this is the response, and quite often you have to make a model. You have to find the best Y. Learn from the data and figure it out. Now, what the energy model way of thinking says, and I'll just deliberately, even though X is a vector space, like in other words, X belongs usually to some d-dimensional data representation, but for simplicity, we'll just represent it as one axis and Y as another. Now, what we are saying is that if you look at this space, you see the contours of something called the energy function. An energy function, which is a function of X, Y, and a model, a sort of a latent thing driving it. And what that latent thing is, think of it as something that the machine has learned, or a proxy of a world model, or its understanding of how X and Y respond to each other. Right? So what happens is that given the right parameters, it is, or just think of it as some function of X and Y. It is some energy function based on X and Y. Right? Now, this function is often called the energy function. It will have some shape. Something like that. And its contour on the ground will look like this. Like in this particular case, the contours or the shadow or the projection down on the ground would look something like this on your X and Y thing, right? So this projection on the ground, the contour, is what we are looking at here in this. And it's obviously, I'm giving just a high level intuition. What it says is that you need to find that energy function, learn that energy function as a world model or whatever, is that so that the actual data points, so the data points are in black. These are real data points, real data points, xi, yi, these black dots, these ones are there. And what it says is that these data points, they should exist here in the minima. Most of the data should be around this, and it should form a function, sort of a manifold, the energy manifold or surface. Its projection down should be such that the contour, these data points should all be residing in the minima, in the valley of that function, right? So let me put that intuition here. So it's almost like a Yosemite Valley, right? Around it are the high mountains. You have the half dome and all of that. Those are the energies, high energy things. And the real data should reside in the valley of the energy function x1. Are we together? What it means is that given a x, so implication, given an x, right? That is a real x, given a x that itself is realistic. So if you look at this picture, not all x is realistic. For example, at this value where I'm drawing my dotted line, there is no real data present, isn't it? Given that is realistic, then x and non-realistic, the energy function should be high. The value should be high. Are we together? It should have high value, whereas x realistic, that is belonging to a real data point, should be low, close to lowest, or right, near minima, low near minima. Does that make sense? So in other words, what it says is that one intuition that people often give is that this energy function should be very uncomfortable with unrealistic predictions, right? And very comfortable and low energy with respect to actual data predictions. So if you could find that, then in effect, you have built a model. And these models, this energy function model that you've created, is, you realize, and these are, roughly speaking, and I'm simplifying a little bit, but not by much, these are called energy-based models. So that is the gist of energy-based models, that they try to represent a function such that all real data, the actual data, presentation data or training data, happens to be sitting in the valley of that energy function, right? If you think of that energy function as something like your Sierra Mountains, and then that all the data would be sitting in essentially the Yosemite Valley. Yeah, go ahead.
So high energy means high loss, and low energy means low loss?
No. So Albert asked a question, does high energy mean high loss and low energy mean low loss? Two things, no. Yes and no. It turns out, see, it's a way of thinking about modeling reality. Having said that, so energy-based energy and loss are different quantities. Having said that, conceptually, so now practical reality is very often during the training phase, the energy function and the loss function are closely related. They are almost the same. Right? It turns out in some situations, but you shouldn't think of it like that. Loss is more a measure of error. Right? Whereas energy is a different way of visualizing a surface such that data points reside in the values. The other important thing to remember is that, see, you do the gradient of the loss, gradient descent of the loss, to learn training. During training, one second, I'll continue. During training, you would do weight is equal to the previous value of weight minus alpha of the loss, isn't it? This is the classic gradient descent equation. And descent. And then all things like atoms are, let's say, much more college-educated brothers or cousins of this simpleton gradient descent loss, gradient descent optimization of the loss, isn't it? Now, loss comes in during training, but the energy function, once you know it, you can actually use it to find the optimal solution sometimes at inference time. right? You could do gradient descent on the energy function during inference when you have completely learned the energy function. Imagine that E has been learned. E and therefore F has been learned at inference. You can still do gradient of E. Why? To find. So suppose, and I will come to, I'll take questions right after that. Suppose you know this energy surface. You have X, let's say X. Theoretically, I could start with a random prediction at inference time and then gradually come down to the correct, let me use another color. I could, let me use this. Imagine that I started with this value. I need to predict what the Y should be. I could start here and I can take the journey to this at inference time. Do you see that? Right? So that is the difference between an energy and a loss function. A loss function is used to train the model, whereas an energy function can also be used at inference time to find the optimal solution. Right? Now, the way this is relevant is, and this picture on the left makes it clear. So imagine that you're looking at, let's say, video. You're looking at a frame here, right? This frame says an apple, let's say, is falling off a tree, right? Then the Y state, so this is current one frame. And you have to predict a future frame, predicted frame. Now what you could do from an energy-based model is, there are many possible things. The apple could be going up, could be going sideways, and there may not be an apple at all. Suddenly you may replace that picture of an apple falling off a tree with the picture of, let's say, a truck driving, right? Or a house or a lake or whatever it is. But the idea is, if you have learned a good energy model, then the Y, the frame that should follow, the predicted frame, should be the one that minimizes the energy function. So you should look in the value of the energy function to search for the plausible Ys. Does that make sense? But how would you do that? And that's the main point. You can do that by starting somewhere, and you can just do a gradient descent if you want to the right value of Y, right? And you can do it in time and space. If you do it in time, you're doing it in video space. If you're doing it in space, so for example, if you have a patch in an image, this patch, and you want to infer what is in this patch, an energy model can help you do that. What is the best continuation to the adjacent patch? Right? And that is the basic intuition. We have a question.
So I was just wondering if, typically in the old school of doing things like you have the joint distribution that you model, and you can like find the joint probability is like a combined function. You could
Yes.
put it that way. You could think of this as like a maximum likelihood estimate. Maybe is it like one form of an energy function, like the reverse of that? It's just something that
Yes.
a connection that came up. So
Yeah, that's a good question, actually. So let me repeat it for the audience. Please remind me your name.
Lavanya.
Lavanya. Lavanya has asked this question. You're still here. I thought you were about to go back to one.
Yeah.
Okay, nice to have you here. So she asked this question that when you do a joint distribution between input and output, you learn the probability X, Y, a joint probability distribution. Then what happens is you find the regions in the probability space which are more likely to happen. Right? And so, in effect, you could, the old way of thinking would be like this. Suppose you have a probability energy distribution. Isn't that somehow related to this energy function? And the answer to that actually is, it is closely related. and there is more to it, but in a very oversimplified way. See, if you take the function, energy function, and you take divide by a partition function, you're literally getting a probability distribution. So from the energy function, you can derive a probability, joint probability distribution. A very, very oversimplified way. I'm deliberately putting it like that, but we can talk more about it. But there is a relationship. So the beautiful thing with the energy function is, if you treat it as a core idea, other ideas that are traditional can be derived from it. That's the way to think about it. So, but I'm trying to avoid all of this partition functions and so forth, because that gets a little bit too technical. So now that is the main idea that is behind energy models. And I'll like one way that people, so that is it. One way that you can say is that suppose I am going like this, and let's say that the car is here. Suppose that there is a latent fact that the machine does not know. Like, you have to predict where will the car be next. But there is a latent fact, namely there is a curve in the road. Then it wouldn't be here where you would normally expect, I suppose, just from inertia. It will instead be here, isn't it? It would turn with that. So that's one way or intuition of thinking, that energy functions, to really discover what's going on, you have to know some things that is not just visible in the input and the output. Input is, okay, input output may just say it was here. Why was it here? Sort of the why or the explanation. There's always a latent reason, a latent variable explaining it. That is the Z. And you just have to find that Z, that explanation that minimizes our situation expectation. And therefore, that set of weights that help us do that. The model should create that thing. That's a hand-wavy argument. Now, this paper, I'll finish this paper. We have covered these models before. All it says is that the joint embedding part, and we already did in the V-JEPA paper, that the right approach, after all is said and done, is that you take the input and you project it into the latent space. You project the output also and project it into the latent space. Then you get a joint embedding. And anything that you do it in the joint embedding space. And when you build predictive models and everything, do it in the joint embedding space. Now, one thing that this paper makes quite a bit about is that, see, when you train models, you start out with data. Let's say this is your data. And you have discovered through some learning a model like this, something like this, a low energy model. Now, the way people improve upon such a model is they apply contrastive learning. Remember, contrastive learning is that you given an example, given a data point, let's just say X, you give it a similar data point that is likely to be present and something that is not likely to be present. Right? So what happens is, if the data points are given, so X and a similar point adjacent is easy to give. But finding non-existent or non-realistic points gets a bit harder in high dimension, because there are so many directions that you can go. And high dimensions tend to be very sparse. So you have to generate a lot of negative examples. Because if you say, this is a negative example, what about all these other directions, which might be positive examples or negative? You have said nothing about that. And so the machine may start, machine needs to be taught that not this, not this, not this, not this, not this. So one problem with contrastive methods is you have a huge problem of data generation. The second problem is literally that too many, it's just high dimensional space, and they're related. High dimensional spaces are too sparse, too much of data generation needs to be done, and you have the burden of data generation. So he goes on to say it in a crucial statement here. Contrastive methods consist in using a loss function whose minimization has the effect of pushing down the, and this is okay. The contrastive sample should be picked in such a way as to ensure the energy assigns a high energy, etc. There are many such contrastive loss methods. Now, somewhere he goes on to say, yeah, contrastive methods are very popular. For example, if you guys have done semantic, like a semantic search, you know that you train the sentence encoder with a contrastive. So they have been very popular. But there are two main issues with contrastive methods. First you have to have a scheme to generate the data. You have some trick to get those data, which can be expensive. And the second is, in high dimension spaces, high dimension spaces are just void, mostly empty space, too much space there. Too little data, too much space. If you have 100 million data point, you may feel pretty good about it, but give it 1,000 dimensional space, 100 million data point begins to look very sparse at that particular moment. So you have to generate a vast number of contrastive samples to ensure that energy is higher in all dimensions. Right? This is the argument I was making. And so it's not a good idea. And it's sort of so in contrast, what this suggests is something, I think, a much more elegant idea. So let's look at this picture. If you look at this picture, what is the problem? The initial picture, just energy-based model, covers this. You see this space between the two data sets. In a way, data goes like, how should I say? Like data is going like this. And like this, isn't it? There is a lot of space between these two data valleys, but a basic model would just cover all of that area. A contrastive, on the other hand, will do something much more weird. It will create a surface like this, contrastive sampling. And you'll have to create a lot of samples to cover points in between, and still it will not be effective. But you take an approach that says, that's a very elegant geometric approach. It says that the valley that is there, how do you have the least amount? So if you want to say Yosemite Valley, then you would say the surface area of the Yosemite Valley. In higher dimensions, the volume. The volume of the minima of the data in that function space, that valley that you have, how can it have the least amount of volume? Volume would be a generalization of what you would consider valley surface, isn't it? So you notice that in this picture, it really is occupying the least volume. Right? You have found a minima which essentially shrink wraps the data, and yet is the valley in the F space. Surface. Isn't it? I hope this intuition is clear. It's making sense. And that's the main idea. And to do that is a regularization method. And what they are proposing is that this journey is okay. This journey, on the other hand, this journey is not okay. Is not as good for all the reasons we talked about. Once we get this, now all of this is pretty high level. Now comes the actual way of doing it, which is the core. And we saw it in the V-JEPA paper very clearly, but I'll just go over it a little bit. Given an input, you encode it. So now this region, this is the region of, remember, everything here is happening now in the latent space, isn't it? So if you think images, you're no more in the pixel space. Do you see that? You have taken an input, which might be a picture or patches of a picture or patches of a video, and you have used an encoder to project it into the latent space. So input has become SX, right? It is the semantic representation of X. Likewise, the target has become the semantic representation of the target. Now what you do, and this is the core intuition, right? If you're saying that, see in a picture, I suppose I want to elaborate this, that if you have a cat, and then suppose you have created a patch. This is your, let me just take this. This part is your input. And you have to predict, let's say you have to predict this part, the other half of the face and the tail. Typically what people do is that people use generative methods to fill in the pixels. One of the problems that you often see with these generative methods is they have trouble dealing with the fingers, right? And things like that is because, and they are in the pixel space. And in a way you can say that, see guys, before you make a prediction, isn't it utter common sense that first you project the data in the best representation space, the best representation in some latent space, right? The most meaningful semantic representation. Because if I instead took this part and did this is your X, did the semantic representation of X, right? And then from that, it would be far easier to predict the semantic representation, let's say of A and B, SA, and from this, SB, a prediction of the semantic representation of this. Does that make sense? Isn't it?
Do it in latent space.
Do it in the latent space.
Oh.
Right? Do it in the latent space, because latent space is where the meaning or the semantics of the is captured the best. And in a way, if you're familiar, for example, with semantic search, you see that happening. If you are searching for something, you don't search in the word space. You go into the vector embedding space and search for it there. Right? So a very similar argument is being applied to images here. And there you ask yourself, make a prediction, and then of course you can have a loss function. How far is your prediction from reality? And then you could use a very simple loss function. As in V-JEPA, you notice that it used quadratic loss or L1 or L2 loss to do that. For videos, they use L1 loss. I think in images, they use L2 loss, but you can do that. And then what they found is, if you do it like that, the idea, it turns out, works. Not only that, it's very energy efficient. You can train the machine in far less data examples, okay? And so on and so forth. So that's the gist of this paper. And now I'll go back to the V-JEPA paper as a quick review. So what were we doing here? Now that we have the background, look at what we are doing. You're doing exactly that. Suppose you take a picture and you occlude some parts of it, mask some parts of it, or literally that picture I made here. So let's go and review this. You take a context picture, there's the orange block, and you have removed half the face and half the tail. Then what you can do is you can encode it. Then you have to send it to a predictor, and you have to say, predict what is there in the masked areas. So you give, the latent feature you give is essentially your masks, the positional encoding, and some learned latent vectors, and you predict what it should be. And you compare it to the encoding of this. We went through all of this in the past, and this is literally a realization of that JEPA core idea for images. And now, after that, when we come to V-JEPA, you'll realize that V-JEPA does exactly the same thing for videos. All we have to do is, video is a sequence of frames. So you have to not take little patches of area, but you have to take little patches of volume, because there is a temporal dimension, isn't it? So you have one frame, then you have another frame, you have another frame. So what you can do is, you realize that they span a volume in pixel space, right? There's a time dimension also. So when you take patches, take out cores of it, like sections, volumetric sections of it. Are we making sense? So it's a very straightforward generalization of image idea to the video idea. And it works. It works. Do you see? By now, this picture looks, I hope, dead obvious. What are they doing? They're taking, again, occluding some or masking some volumetric parts and then projecting. Now, you have to be careful. You can't randomly take out voxels or volumetric spaces, because suppose you randomly did it, then what would happen? In a typical video, the frames don't change much from frame to frame, right? You have about 60, let's say 20 frames. So if you randomly take out, the machine will be very clever. It will just go look at a future frame or a past frame and infill the missing parts, isn't it? So when you take out sections, you have to take out across all those frames. The whole temporal sequence, that masked area, has to be taken out, like a code, like a sort of a tube has to be taken out. A rectangular tube of space has to be taken out in some sense. Does that make sense? Right? Otherwise, it will just look ahead and fill it in. You have to be a little bit clever, otherwise the machine will be clever on you. Right? Now, one of the things that I mentioned that, one of the things, if you remember, how did we do that? X goes into, and this was, I mean, of course, if you're familiar with the VIT, it went into the simple VIT encoder. In practice, then Y went into, again, a VIT encoder, and then you had this went into, then you added, I'm just simplifying it, the position X, SX, plus the latents came from the position encoding, and from learnable vectors. Ignore the technical details if you miss that, but it goes into a predictor, and the predictor, would predict S hat Y, and a little patch of the image which you had occluded, which is your Y, goes into this, and SY comes in, and all you do is you look at the distance between SY hat. This was a technique that was used, right, to train this machine, and it worked. And pretty much you see exactly the same thing happen in this particular picture, right? And now, one of the things that we had in that picture was that, hey, what is our objective? How do we train this machine? A naive way would be to say that whatever your encoder model is, if you use an encoder model, E theta, and then it produces something, this is your delta Y that it is saying, then minimize the gap between the prediction and the actual encoding of the reality, isn't it? But actually that doesn't work, because your predictor model can become pretty smart. What it can start doing is, the encoder model can become smart, and it may degenerate into the situation. What happens? So imagine a situation in which E theta X, invariant of X, always produces 1. So therefore, E theta Y will also be equal to 1. No matter what you give it to that, or it just produces a constant, some constant, right? Then what happens? Do you realize that this whole thing will easily minimize to 0? Right? This thing will learn to be clever and minimize to 0. So it will lead to trivial solution. Like you don't get a good answer. So the way to prevent that is you don't let, when you back propagate, or this is a back propagation. And by the way, this is not invention of this paper. It's been there from before. People learned in computer vision that when you train the model, this will produce your loss. You take the gradient of the loss and you back propagate it in this direction. But in this direction, you break it. SG is often stands for stop gradient. Means during back propagation, don't let this encoder, the target encoder, don't let it learn from the loss. This loss, or the gradient of the loss, should not update this encoder. So then the question is, how will this encoder learn? Well, there's a certain bit of mathematics that shows that the best way to train this encoder is by taking the moving average weights of the input encoder. And we talked about it. So what it will do is, the target encoder is always a few steps behind the input encoder. And the basic idea is, what do we gain by that? You want to make sure that the predictor network, which is another VIT network, is far ahead. Like it is far ahead in learning than the encoder. So the encoder doesn't get time to cheat, right? Or come up with a trivial solution. It's sort of a bit of a mathematics that goes into it. It is true, by the way, here as well as in the V-JEPA paper. And in this paper, they sort of mention it. It is there in this sentence that they mention. The hypothesis is that incorporating an exponential moving average to compute the representation of Y ensures the predictor evolves faster than the encoder and remains close to optimal, therefore preventing collapse. So when you end up in a trivial solution, when the machine doesn't learn anything, you call it a collapse, right? So it prevents such a collapse. So what is really going on in this paper? By now, it looks very simple. We have explained all the steps. You take it, you create little volumetric patches, except that these patches are not surface areas. They're not 16 by 16, but they are 16 cross 16 cross something, 2. Let's say a minimum is 2, and then you create these patches. Then you remove some mass tokens, some area you say, okay, these are the targets, right? And the rest is the input. So given an image, some part is the input, the white is the input, and the blacks are the masked. So if you look carefully in this image, I can't zoom. Look carefully at this. Do you notice that the blacks have been staggered in such a way that the machine cannot cheat, right? It cannot just look ahead and fill back, right? And so you use this technique, and then what you do the standard thing. The X's are put into the encoder. Then what do you do? Very much like the V-JEPA, you feed it. You bring back your mass tokens with their position encoding and some learnable vectors to make a prediction. Whatever prediction comes. Now the interesting thing is here you use L1 loss. L1 loss means just absolute value loss. A minus B absolute value loss. That is it. Stop gradient just means the back propagation should happen only in this direction, not in the forward direction. You never use the gradient of the loss to train the target encoder. That is the main point they are making. And when you do all of that, the rest is everything that we know. And the results are spectacular, very, very good, actually. It is surprisingly good for a research idea to become a first generation implementation, a straightforward implementation in video, and for it to straight away go and achieve state-of-the-art results is very remarkable. Right? It is very remarkable. You can see the benchmarks, they speak for themselves. You see that in most situations it achieves pretty good results, right? You look at the V-JEPA results. It's pretty good. It's either state-of-the-art or close to the state-of-the-art, right? In most benchmarks. Sometimes it beats the state-of-the-art significantly. Sometimes sort of comes close to it. So, this is still at a first draft idea, first draft implementation. It's open to a lot of iterations and improvements and subsequent papers. And you can see that now here comes the thing. How do you verify that this actually works? What they did is that now you have to decode it, right? You have to get back to the pixel space from the latent space. So what they did is something very interesting, but actually it's there in the appendix. Let's go back to this beautiful paper, this beautiful aspect. So, and the appendix is pretty extensive, but I suppose these days, most of the meat of the matter or the real core of a paper is pushed down to the appendix. It used to be that it would be in the method, but these days, papers start with a very short, brief method, quick read method, followed by results. And then after conclusion and everything, you go back and in the appendix, you find the method. So let me see where that picture is that illustrates that, because it makes an important point. And of course, OneNote has stopped cooperating. Okay, here we go. So once again, it's freezing on me. Give me a second, guys. Oh, yeah, here we go. We got the paper back. Appendix. No, it is not in the appendix, it turns out. Oh, yes, it is here actually, not in the appendix. I apologize. Here, what they mention is, look at this region. This was the region that was removed. This is the target that you have to predict or fill in, right? So as you go, the prediction will be only on the target. What they do is they train a diffusion model, and you don't give it the rest of the data, the X, you only give it the Y hat, the SY hat, only this. And you ask, if this is your input, produce the image, go back to pixel space. And you notice how well, if you look at this dog here and how well it sort of goes and fills in the rest of the face and the tail in the video, it does go and do that in a very credible way. And there are further visualizations that show the same thing. So in other words, this whole thing works, and it's very efficient in the sense that they use the word label efficient. In other words, very easily you can create data patches, etc. And the amount of training data needed to train this is literally a couple of orders of magnitude less than what is used to train more traditional methods.
So even the masking, the original picture is random, or is there any?
No, you can just use heuristics to easily mask it. So that's it. Simple masking and so on. You just have to be consistent. Like I said, that it's a volumetric space, like cylindrical space, sort of a rectangular cylinder in the temporal space you have to take up. So I'll conclude this. I hope we covered this paper. The way I would say it is that JEPA was a thought position paper. That's one way to look at it. There will be perhaps a lot more development on the JEPA idea, but the two realizations, I-JEPA and V-JEPA, are certainly quite remarkable. And the fact that they succeed, that in real world they produce results that meet or beat the state of the art, perhaps is a testament to quite a bit of validity to the ideas proposed in the original paper. So obviously there'll be more evolution. I look forward to more papers. We should all look forward to more development like this. But the point to note is that it's a purely predictive model, not a generative model. They've managed to, what they're arguing for is, at core what they are arguing for is that guys first do representation learning using a good encoder. The ultimate goal is to train a good encoder, isn't it? But why would we train a good encoder? Because a good encoder can project data, images, videos, etc., into the right representation. Because if you first have the right representation, then your predictions are much more meaningful. And that is the right way to go about it, right? And in a way, that encoder is what has some resonance with this idea that the machine should develop a whole model. That is that. So with that, I'll conclude this V-JEPA series of papers. Now, there's an interesting irony, by the way. This paper was submitted for a conference, and ironically, this paper was actually, this V-JEPA paper, believe it or not, was rejected. It was not accepted for the conference, and and you would be very surprised. It's quite a wonderful work, and yet it was turned down. And obviously, papers are accepted or rejected. Little bit depends on the reviewers how strict they are and so forth. The one valid point the reviewers did make is that the V-JEPA paper did not sufficiently take care of the temporal nature of videos. It could have leveraged that more, so that work needs to be done. And the second point that they mentioned was that it is such a straightforward extension of the I-JEPA and the main idea of JEPA itself that it sort of is somewhat deficient in novelty. Like it's sort of a no-brainer kind of extension. So, so I suppose with more work, it must have gotten accepted somewhere. I don't know where, or where it will be published, but it's certainly a remarkable paper. And so I'll conclude our discussion on first the thought paper. So just to summarize, what did we cover? We covered the JEPA thought paper, these big ideas that we did, which is quite theoretical in many ways, but see, great things are done, or big changes happen when somebody comes up with a completely different formulation of how one can go off the beaten track. This paper is a call to move off the beaten track. And then it does get realized in the I-JEPA and the V-JEPA paper, both of which resoundingly, I suppose, endorse the fact that this idea has validity. Right? It does work in real life and can be used. So, but obviously, my feeling is that this is the beginning of things to come. Much more research needs to be done. Much more developments will happen in this space. So let's look forward to more papers. With that, I will open it up to questions. Any questions, guys? Or was it clear? Was it reasonably clear?
Thank you.
All right, folks, I am not getting any more questions from the audience. I'll stop the recording. Thank you for being.
Can you hear me?
Oh, yes, I can hear you.
Yeah, perfect. So the question is in my mind is that the joint, we are taking the input as well as the output, and there are two spaces, and the joint spaces are being explored together.
Yeah,
right.
You project both input and output into the same latent space, and that is the representation learning sort. And there you do your activities, your predictions, your loss function, your everything.
So the two spaces is normally in a regular, only one space is considered, right? Not the
yeah. If you look at the generative models, right, it's a little bit. You stay in the pixel world, right? You say, generate me more pixels, infill this gap.
Right. So the distribution, there are two distributions here. One is in the input space and the latent space, and one is in the output.
That's right.
The loss function is only applied in the
latent space.
In the latent space, exactly. Okay. And we are exploring both the distributions at the same time, actually.
Right. We are saying that think in the latent space, and the real space will take care of itself.
Right. Okay, that's very interesting, actually. And then the point that you made that in high dimensionality there is a lot of sparseness And can you explain that? That was a little bit. I understand that lower the dimensions,
It's
you have.
very easy. Let me explain it in this way. I'll give you two, but before that, let me just explain this. Have you noticed? Think of 10 friends of yours who are not in your neighborhood, or 20 friends, and ask yourself, how many of those friends happen to live close to either a state border or next to the sea?
Mhm.
You'll be surprised how many, it will be more than you think, always. Close your eyes, think of remote friends all across the country. And now ask how many of them are close to either the sea or a state border.
But
And
that is how most of the civilization is, because it was mostly the waterways that and the roadways that brought us together, or make
okay, forget the
communes
sea.
happen.
Or forget the sea. Just imagine that you're in the heartland of US. Now still imagine lots of friends who are in the heartland of US. You'll realize that many of them are rather surprisingly close to the border. Right? There's a geometric reason for it, which is non-historic. The point that you make is true. Civilizations form next to water bodies. So therefore, I've taken water bodies out of the equation now. Now, see, here's how to reason about it. It's quite simple. Suppose I give you, I'll give you two reasons. Suppose I give you 1 unit distance, 0 to 1, and I give you 10 points or 100 points. You will have great difficulty. They'll all be crowding in the interval 0 to 1. Isn't it?
It's just the nature of how the distributions are, actually.
That is, no, just look at this. Don't bring in any assumptions. Very visually, they will all be crowding along that interval, 0 to 1 interval. There isn't any other place for it to be. It has to be in that one dimension. Right?
Mm-hmm.
Now, the moment I go to 2 dimensions, the same 100 points, now they sort of diffuse off and they spread out a little bit more.
Mm-hmm.
Because they have one more dimension to spread out. Obviously, it's a little bit, 2 dimension is a little sparse compared to 1 dimension for the same 100 points. Now go to 3 dimensions. What will happen? The same number of points will diffuse out if they are uniformly randomly distributed. Now they will begin to get the same 100 points will occupy the same unit cube. This is 3D and still unit square, unit cube. They have gone out. And do you notice that the same data points are beginning to look, in 1 dimension, they look dense. In 3 dimensions, already they are beginning to look sparse.
Mm-hmm.
And imagine what would happen by the time you go to 1,000 dimensions. They all look like little stars separated by intergalactic space.
Mm-hmm. Like just the entropy of it, actually.
Yeah, that's right. Another way that you can explain this is imagine people lived in a disk and you lived in the center. Right? It's a unit disk.
Mm-hmm.
One. Now, let's say that you have 100 neighbors, or to meet half your neighbors, how far would you have to go? You would say, well, I can go a distance r such that the area pi r square, this cross-section area, is pi r square divided by total area, which is pi 1 square, is equal to just r square. Isn't it?
Yes.
So r square should be half, because I want to meet half my neighbors. And so r should be 1 over square root of 2.
Yes.
That's good. But now, suppose all your neighbors, you're still sitting in the center, but they are like little particles that are in a unit sphere. This is a disk, this is a sphere.
Mm-hmm.
Now, again, 4 by 3 pi r cube divided by 4 by 3 pi 1 cube, because this is unit. This is the ratio to get, that has to be half, right? And so what it means is r cube has to be half in 3 dimensions, right? And so this is, now what is 1.4, right? 4142.
Right,
Is that
1.4142.
correct? And that is approximately equal to 0. Do that, guys.
Do 1 by 1.4.
Yes.
Okay, so distance to
0.7.
traverse is increasing now to meet
That
half
is right.
of your friends.
Yeah. So Shirin, just pay attention to this, because there's an important point I'm making. So this, is it approximately 0.7? Right? Now, what it means, even in 2 dimensions, it means that to half of your neighbors live in 0.3 distance from the edge, isn't it? Which is the point I was making, that if you really think about it, even in the heartland of America, right, more than half your friends would be living, right, would be living actually pretty close to some border. Now you see why I was making that statement. People have observed and remarked this fact. And now in a sphere, it becomes even more. R is equal to 1 over cube root of third root of 2. Right? What is the cube root of 2? Anyone remembers? So how far do you have to go to meet half your neighbors? The cube root of 2 is approximately what? Anybody?
No, the only intuition is it will be much closer.
Tell me if this is correct, guys. Those of you who have a calculator.
Yeah.
Right? And so what is it? Look at it. To meet just half your neighbors, you have to go practically to the border and bring them all in, because the other half, they seem to be practically living on the border, isn't it? So what happens is that it's a very peculiar fact, actually. In high dimension space, wherever you are, the notion of neighbor begins to collapse. So when suppose you are dealing with 1000 dimension, right? You are looking at 2 to 1000, right? The distance that you, in other words, to you, it will always look that all your neighbors are running away from you in high dimensions. They are all sitting on the, they are all sitting on the edge of this hypersphere. It's a high dimensional spaces are very non-intuitive, guys. We take it for granted. These days, we don't think twice before creating a vector embedding in a 1000 dimension space. Yeah. But actually, human mind has a very poor intuition of high dimensions. I just took you from 2 to 3. Already you see that you couldn't even get your intuition right in 2 dimensions, which you see, or 3 dimensions, which you see. And so you should go with the underlying fact that you have practically zero practical or real experience or intuition into higher dimension spaces. Higher dimension spaces are weird, and they're mostly empty. And all the, with respect to any one point, all other points seem to be far away. Right? That is how higher dimension spaces behave. They're little strange things. And we have only actually begun to gain an understanding of them.
So what does it imply in a high dimensional space? Most of the neighbors, half of the neighbors are away, but so what exactly means to the model? I mean, training, what exactly
what it means is that the notion of neighborhood breaks. So think about it. The point that this paper, for example, makes is contrastive learning. Means if you have a valid data point, you need a good training example would be something nearby, which is unreal. Because you say this is real, this is unreal, isn't it?
Yeah.
But what is nearby when everything is so far away?
Yeah.
Do you realize that? Yeah. It becomes much, much harder to generate points, and you have to generate a whole lot of negative examples.
So the training time, and of course,
Training becomes ineffective, right? It just becomes ineffective, which is why it makes a strong argument in the other paper that you should use the what he calls the regularization method or the geometric method of minimizing the volume of the minima, the valley.
Yeah, by the way, the cube root of 2 is 1.25, even worse than what you have.
Yes.
1.25, not 0.85. Yeah.
No, 1 over that.
Oh,
1 over 1.25. Because it's a square, then
oh,
you
yeah,
have to.
in the denominator. Yeah.
Yeah, it's about 0.85, isn't it?
Yeah.
That's what I was saying.
And one other thing, as if in the position paper where you're looking at the entropy graph, I think further down. So you had said about inference. At inference time, you are searching that low energy space.
Yes.
So I couldn't quite follow that one. So how would I kind of missed it. So I would expect the prediction already should be in one of those black dots in the energy model, right?
No, what energy model helps you build is during training time, you can use your loss function to construct the energy surface. Once the energy surface is constructed, the beautiful thing is that at inference time, you can sample off that energy surface. You can look into the valley and pick any point with that X and Y and possible Y, which is in the valley, as a potential solution.
Oh, okay.
And you can discover that by, when you tumble, how do you do that? You basically tumble down to the valley, right? To go to the valley is to do gradient descent at inference time.
Oh, I see. Okay.
Because all you have is a function. How would you know if you're in the valley or not? To get to the valley, anyway, you have to walk, you have to sort of climb down to the valley, tumble down to the valley. And therefore, energy models, their unique feature is that they let you do gradient descent, not just for training, but or learning, but actually at inference time, finding amongst the possible solutions, the best solution.
It's less efficient, right?
It's more computational, which is why energy models are, if you look at most textbooks, they do not even teach you energy models. Guys, 1 second. This is OneNote has frozen again. I'll restart it. But they're very powerful. They're very powerful. And the time has come, I suppose. If you look at these people, the luminaries, they keep bringing in, and a lot of these ideas, let's put it this way, they tend to use ideas from statistical mechanics, physics, energy, far more than mainstream people do. If you look at whether you're looking at Geoffrey Hinton or Jan LeCun or any of these people, they tend to use physics-based arguments a lot more.
And again, like it sort of brings back the analogy of like Bayesian models versus like you get the distribution and then you have to like sample from it if you want to. That
is true. See, Bayesian reasoning has always been there, but again, if you think of Bayesian statistics and argue why is it not much more widespread, at the end of it, it comes down to the fact that it's computationally a little bit more brutal. Right? You have to go on, for example, do MCMC, right? The metropolis all over the place. Before you zero in and come up with a posterior distribution. So obviously you need compute power to be able to do that. And in many situations, people thought non-Bayesian reasoning itself is enough. But there are situations where you can't avoid it. For example, hyperparameter tuning. If you can't do gradient descent, because there is no differentiable function, hyperparameter tuning, for example, how many nodes should be there in a very simple neural network? How many nodes should be there in a given layer? How many layers should be there? Right? What should be a learning rate? What should be the dropout rate? What should be this? What should be that? The moment you create a neural architecture, it will be infested with hyperparameters. You're again looking at a very high dimensional space of hyperparameters. And to boot, there is no gradient descent that you can do because it's a non-differentiable space. So what can you do? There were pretty idiotic methods like grid search that textbooks teach you, elementary textbooks in machine learning teach you, right? But the right way is you can now do a Bayesian optimization. So Bayesian optimization now doesn't look so foolish anymore in those situations. It seems to be the right way to go.